In this section, I'll discuss about alkyl halides, naming of alkyl halides, and the reaction that leads to formation of alkyl halides, and a very important type of reaction given by alkyl halides is called Grignard reactions. So we'll talk about all these. Just to remind you, alkyl halides have a group like this and a halogen at the end. So let's assume that my halogen is I. So this is an alkyl halide. These are examples of, like, this is methyl chloride, and this is ethyl having two carbon, ethyl bromide. So how do I name these compounds? Just like naming of any other organic compounds, select the longest carbon chain that must contain a double or triple bond when they're present. And numbering should begin at the end closest to a substituent group. Again, there's nothing new about that. If substituents have the same distance from each end, alphabetic priority is considered. And also, substituents are named in alphabetic order. So if this molecule is given, first you get the longest chain. So this is the longest chain. And the longest chain has 6 carbon atoms. And substituent groups are the groups that are directly bonded to the longest chain. This is the methyl group, bromine or bromo, other bromo. So numbering has to begin from the end that would be closest to the first substituent group. So in this case, second location you have Br. So that's why we started numbering from the left hand side. So 2, 3 dibromo, because both locations have bromo. So di means 2. Dibromo, then 4 is the location of the methyl group, hexane. So you also see that we gave bromo, we wrote bromo before methyl, M. Now we discussed this reaction in previous chapter, one of the previous chapters, alkene with reaction of an acid, HCl, HBr, HI, even H2O. We talked about Markovnikov's reaction. Now, in this particular case, you're seeing a reaction of alkene with HX, where X could be Cl, Br, or I. So just like any other Markovnikov's reaction, H goes to that carbon with double bond or triple bond that has a larger number of hydrogens. So this end of carbon has larger number of hydrogens, already 2 hydrogens. So this hydrogen would go there too. And X, which could be Cl, Br, or I, would go to the other end. That's how you end up with this product. Alkenes can also react with halogens, giving alkyl halide. And we discussed that in the addition of halogen to alkene, you first get bromonium ion, chloronium ion, iodonium ion, which is a triangular complex. So let me show you that in case you forgot that we discussed before. So C, 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 and then if I have a Br getting bonded, then Br makes a triangular complex. This is called bromonium ion. And then the other Br gets added as Br minus. So Br minus would be attracted and would try to avoid this path, which is occupied by bromine. So because of a steric hindrance, it tries to avoid this. It's not going to happen. Rather, it would go from the opposite end to this end, and in other words, anti-addition product takes place. We discussed that before. In next slide, we're showing you how you can get alkyl halide from an alcohol. Now, alcohol, in case you don't remember, is you have like a carbon, carbon, carbon at the end. You have OH, that's alcohol. OH attached to carbon gives alcohol. Now, we have been using R to represent any alkyl group. In this case, this is the alkyl group, 3 carbon propyl group. So it's propanol, what I have drawn on the top. Now, alcohol reacts with HCl, giving alkyl halide. Now, this kind of reaction will happen only for 3 degree. So what the alcohol that I've drawn on the top is not a 3 degree. It's a 1 degree alcohol. Why? Because this is the carbon that holds that functional group OH is bonded to one other carbon, which is this carbon, and that's why it's a 1 degree alcohol. For 1 degree alcohol, the reaction is this, part B, thionyl chloride, if you want to replace with Cl. So if I want to propyl alcohol or propanol to propyl chloride, I need to use SoCl2, that will give me CCCCl. If I want to have Br at the end, CCCBr, I must use PBr3. So keep that in mind. So depending upon what you want, and you'll have to know what reagent that you need to use. So, and pay attention to the fact that for 1 degree or 2 degree alcohol, these reactions can happen. With thionyl chloride, you can get chloride. With PBr3, you get alkyl bromide. If I have a 3 degree alcohol, it's simply, you can use HCl for chloride, HBr for bromide, HR for iodide. Now let me show you one example of a 3 degree alcohol. So here I'm going to show you what 3 degree alcohol is. Remember 3 degree, the carbon must be bonded to 3 other carbon. So this is 3 degree alcohol. This carbon with asterisk is bonded to 3 other carbon, and that's why it's 3 degree alcohol. So I can simply add HCl in order to get chloride. If I use HBr, I get bromide. So it'd be CCCC bromide. Of course, I left out hydrogens for. So keep these reactions in mind. They're very important reactions. You can also get alkyl halide by using light, ultraviolet light. Ultraviolet light has enough energy to break halogen bond. So if I have basically 2 Cl bonded together, ultraviolet is going to break it down into 2 Cl radical. Radical means the Cl has its unpaired electron. And they're highly reactive and eventually gives you alkyl halide. If you are working with methane and chlorine in presence of light, you'd end up with methyl chloride as one of the products. Now this is a bigger alkane. Again, same kind of reaction with chlorine. It gives you this as one of the products. Now, why we're saying that this is not a good method for this product formation? The answer is very simple, because chlorine could be in here or in here. So they would give you 3 different possible chlorides. On the other hand, if you look at the second reagent, we're saying that this is the high yield, and it's a good method for this kind of product formation. Now, why is that? Make sure you understand this. If I just show you that if each of these carbon the bonded to the central atom has 3 hydrogens, this is CH3 group. So Cl can replace any of these hydrogen and you can get CCl bond like this. Now if it would be identical no matter whether Cl gets bonded to this carbon, this carbon, this carbon, or this carbon. So when randomly this kind of reactions happen, you are going to get the same monochlorination or monobromination product, and that would be in very high yield because other possibilities are not there. This is the only way you can get one chlorine replacing a hydrogen. On the other hand, in first case, there are many ways this can happen, at least 3 possible products you can see. So if I'm looking for a particular product like this, chlorine bonded to the first carbon, then it's not very likely, it would not be in high percent yield. It would be like one of 3 products. Now we're going to discuss about problem number 5, page 226. Basically, they're asking for products of a reaction. Now we discussed about this, but let's do one of these problems. The part B. This is pentane ring, cyclopentane ring, OH, that makes it alcohol, cyclopentanol, and then there are 2 methyl groups. It would be CH3 here and CH3 here. Question is, in presence of thionyl chloride, SOCl2, what would be the product? We already talked about this. Thionyl chloride would replace OH, 1 degree or 2 degree alcohol, by Cl. And this is a 2 degree alcohol because this carbon, let me show you with the red pen, this carbon, which is part of the ring, is bonded to 2 other carbons. And that's why it's 2 degree. And 2 degree alcohol gives this kind of reaction. So I would end up with something like this. Now I have Cl, a methyl group. So I have 2 methyl groups. And so that's going to be the final product. If I use PBr3, in that case, OH would be replaced by Br. So that's how you can get bromide or chloride from 1 degree or 2 degree alcohol. And keep in mind, when it's a 3 degree alcohol, you'll have to use an acid like HCl, HBr, or HI. In this slide, we're going to discuss about Grignard reagents, how we make Grignard reagent, and what kind of reactions are expected from Grignard reagents. As I mentioned before, this is a very important reaction. You just need an alkyl halide, Rx. So R represents alkyl. Aryl means it's a benzene ring. Alkenyl, again with alkene, from alkene, alkenyl. Now, if I have bromobenzene, that's what you see in here, bromobenzene, in presence of magnesium and ether, it forms a Grignard reagent, and that Grignard reagent would have carbon-magnesium bond. So this is the carbon, this is the magnesium bond. Magnesium would have positive charge, delta plus, that's why you were showing you as delta plus, and carbon would have negative charge. And that negative charge carbon is highly reactive and combines with H plus and many other reagents. Like if you add H2O, even from H2O it can grab H plus and giving CH bond. Here we're showing you a reaction of Grignard reagent. First you start with alkyl halide, in this case 2-bromobutane, and in presence of magnesium and ether it first forms this magnesium bromide. So wherever you had the bromine that is replaced by MgBr with a new bond formation between carbon and magnesium. And remember I said that magnesium is metal, so it's from the far left of the periodic table, that's delta plus, and obviously carbon gets delta minus because between magnesium and carbon, carbon is more electronegative. And negative carbon is highly reactive. So G200 is nothing but H2O, except that this is a heavy hydrogen, deuterium oxide, D2O. And one of the D from D2O gets bonded to this carbon, and you eventually get this compound.